Good day. I'm Martin Gago with Market Radius Research. It's Tuesday, July the 19th, 2022. We've got CEO Andrew White and CFO Mark Korol of Char Technologies joining us. Char is a clean tech company specializing in organic waste pyrolysis and biocarbon, custom air and water treatment, and environmental consulting. Happy to have Andrew and Mark back with us. I think Char is a little bit like a duck. Things seem very calm on the surface, but its legs are paddling vigorously beneath the water. And in these situations, it's good to have the company join us to provide an update as to how things are moving along. Char's got some fascinating technologies that should be able to make some significant environmental impact with strong potential economics. Char currently has 4 projects on the go, some with multiple stages. So I'm very looking forward to getting an update on the progress of those projects. But please remember, this is neither a recommendation nor investment advice. We're here to learn about the company. Andrew, Mark, thank you very much for taking the time to join us. And let's see a bit of an overview here on Char.
Absolutely, Martin, and it's always a pleasure to be here. So as you said, Martin, we'll do a quick kind of background, a reminder to those on the call what we're all about, and then we'll talk a little bit of the projects through this short deck, and then we can get into a more vigorous discussion, which I'm looking forward to. So at Char Technologies, we're all about decarbonizing for a circular economy. And what that really means is decarbonizing is all about greenhouse gas reductions and CO2 removal from the atmosphere. And a circular economy is all about taking low value or negative value materials and adding value to them. And through our high temperature pyrolysis technology, we do both of those things at the same time. So as a quick highlight and summary, and then we'll talk about the technology very briefly, and then into the projects. The technology, our high temperature pyrolysis technology, is carbon negative, as I mentioned. It's a modular platform. So as we talk about the projects, we'll talk about different quantities of output and different types of output. But the thing to keep in mind is the technology is modular. So we're still using the same kind of module. In some projects, we have 2 modules. In some projects, we have 1. In some projects, we're making renewable natural gas and some hydrogen, but it's all from that kind of same module. We do have some great existing clients, including Canada's largest flat rolled steel producer and a green hydrogen project with Hitachi Zosen and Nova in California. Patents and IP we can always talk about. And then when we look on the next slide about the technology, we really have 3 market verticals that this technology really has some great competitive advantage for. In 2 of the 3, the business model is really that system sale, so equipment sale and some recurring revenue, just based on the dynamics of those markets. And in one of these marketplaces, our market verticals, we're pursuing the utility model. So that's our projects, that's our build, own, operate opportunities. That's where the long-term and consistent revenue is really poised to come from. Our pipeline of project opportunities is over 100 million now, and we don't have any long-term debt on the balance sheet. So as a quick summary of what high temperature pyrolysis is, this is a graphic. It's a little busy, but we'll kind of walk you through it. As I mentioned, we have on the left here 3 market verticals. Wood and agriculture, that's where we're doing our build, own, operate opportunities. So that's really going to be our focus on when we talk about projects. But the other 2 are biosolids. So that's the sludge left over from a wastewater treatment plant. And digestate compost, if any of you follow renewable natural gas through anaerobic digestion, one of their byproducts is a compost-like material called digestate, or we can use straight compost. Now, what we're showing here is that each of those 3 feedstocks can go into our high temperature pyrolysis system. High temperature means 850 degrees Celsius. Pyrolysis means 0 oxygen. So what that allows us to do is, instead of burn, we don't burn anything because there's no oxygen. We do what's called thermochemically convert, and we always create 2 output products. One is called a syngas. That's the gas we can either use for heat or energy directly, or we can further convert that into renewable natural gas or green hydrogen. And the other is a biocarbon. So think like a charcoal. In some instances, we can use that to offset fossil coal in heavy industries like steel making. We call that a biocoal. or we can create what's called a biochar, and that has land application, fertilizer type benefits, and can also generate carbon credits in voluntary carbon markets. So we're able to valorize two outputs in all of these cases. So at a really high level, that's the technology. Sorry, Martin?
With the, you've got the different types of syngas. Syngas is always on them, and the bio carbon. Are you, and you've got the three inputs. Are there other inputs you could use, or do they have to be sort of just kind of carbon based, or are there some, yeah.
Yeah, no, it's a great question. So kind of a couple of points to make. One, yes, they have to be generically speaking some kind of carbon based.
Yeah.
That's what we like. When we look at a project specifically, whether it's a system sale or our own build, own, operate opportunity, we're always looking at having a consistent feedstock. So when we're building a project for wood, we're going to keep taking wood into that plant. Biosolids, we're going to keep taking biosolids into that plant. And the reason being, we want to be consistent so we can get a nice steady production. Certainly thermal technologies have been applied to things like black bag garbage and more complex heterogeneous feedstocks, and those tend to bring with them a host of challenges. Those are challenges that we're eager to approach once we've really begun to dominate the market in these verticals where there's lots of feedstock. It's very consistent, and we know we can make quality product out of those feedstocks.
Okay, and then on the outputs, are you able to like turn some knobs and dials and so forth on your pyrolysis machine, then to maybe get a different type of biocarbon or biochar or like different flavor of syngas, so to speak, or is it you just do it and whatever comes out comes out?
Yeah, it's a bit of a mix. So the feedstock will dictate a little bit what those outputs look like. So if you see, or if you look closely on the biocarbon stream, where we look at the biosolids, which is straight across, or the digestate, which is at the bottom, we're not producing biocarbon for steel making, for example. We're not producing that clean fire, and that's because the feedstock has a lot of what we would call ash. So ash, from a land application or a fertilizer use is good. It's nutrients, it's calcium, phosphorus, potassium, but those are all things you don't want in a blast furnace. So it's dictated a little bit based on the feedstock, but we do have control. So we can operate at temperatures between 500 degrees Celsius and 850 degrees Celsius. And we can operate in residence times as short as 20 minutes, as long as 90 minutes. And so knowing and, kind of turning the dials and, programming in, how long we want it to run, it's continuous. So material is continuously going through, but how long it takes the material to go through and at what temperature will dictate the yield. So we can create more syngas or more carbon depending on how we change those values, and the syngas quality. So we can create more hydrogen in the syngas, or we can create more methane in the syngas, for example, depending on how we change those knobs. And that'll be dictated by what we want to do with that syngas. Ultimately, is it just for energy? Is it for green hydrogen? Is it for renewable natural gas?
All right, and this is high temperature pyrolysis. There's also, I guess, low temperature or normal pyrolysis as well, and that's just used in different applications or not so suitable for this.
Yeah, so there's kind of a suite of pyrolysis. So there's fast and there's slow. So we're slow, and then within the slow, there's kind of high temperature, and we'll call it standard temperature. So we're not fast. Fast is all about optimizing for bio oil. We don't look at that space. We look at gas and carbon. When you do, though, a standard, lower temperature pyrolysis, generally you can only create one output. So you can create biocarbon. The biocarbon quality isn't as high when you run at low temperatures, and you don't create any syngas that's extra. So in all pyrolysis, we use some of the syngas we generate to run the process, so to run the heat. So we're not, bringing in natural gas or propane or external heating sources. We're using some of our syngas to run our burners. But if you do it at lower temperature, you end up using all of the syngas to create your heat. When you do higher temperatures, you get a lot more gas and you get a lot higher quality gas, which lets you both run your plant and have excess available to sell to the market.
Gotcha. Is now a good time to ask about you, because pyrolysis is an established technology. Just quickly hit your sort of intellectual property and your patents and so forth. What makes you sort of defensible?
Yeah, absolutely. So our IP that we have published and IP that we are pursuing, so it's in kind of different stages of application, is all around process. So kind of if I like to call it the recipe book. So what do we put in? How do we process it? What are the conditions to make specific outputs? The kiln or the high temperature pyrolysis module is kind of like the oven. So our IP that we own internally, that we develop, that we continue to develop, either patents or trade secrets or know-how or the like, is all in the recipe book. And then we have licensed in the oven from what we believe is certainly the best manufacturer of that type of equipment that collaborates really, really nicely with our process. So we work together really well. And then that allows us to do the entire package from equipment, process, everything to produce these syngases and biocarbons from these various inputs.
So you have is it a third-party design, pyrolysis machine that you use, or do you sort of get them to tweak it given your IP and your requirements to sort of the Char version of it?
Yeah, it's exactly that. It's a collaborative process where the kiln's been well established and proven throughout the world in processing activated carbons. You do have to change some design elements to produce or process the feedstocks that we process and produce the outputs that we produce. But that's sort of been a collaborative process to make sure that we're bringing in well-established equipment to connect with our process, so we're not trying to reinvent every aspect of this pyrolysis space. For any company that's kind of bringing new technology forward, one of the biggest names of the game is de-risking. And this is one of the ways that we can de-risk a lot of the mechanical aspects. So, you would think fairly simple things, but, things like the seals to make sure there's no oxygen in the plant, the burner package, how that's designed, waste heat recovery, bill of materials, so we know everything that's going into that, and we can be pretty tight on knowing what our costing is going to be to build a plant, so we're not going to face these huge cost overruns because we missed a couple things, which is it's not sort of a dig at anyone in particular, but it is something that happens on a first of build, right? So we're looking to de-risk it from a mechanical aspect, and we're looking to de-risk it from a project delivery cost aspect.
Gotcha. And just to circle back, you mentioned it's modular. So you use one size pyrolysis machine, and if you want twice that much production, you buy a second one and put them side by side, and 3 times you put a third one in, and so on. You don't make bigger ones, because probably going back to your mechanical stuff, things get weird with scale sometimes, and you can't just double the size of it.
Yeah, there's a couple aspects to it. We do have a couple of different kiln sizes that we can offer. So we've got kind of a small, medium, large, and then you want to go even bigger capacity, you do 2 or 3 or 4 larges in parallel. And part of that is, again, on that de-risking from a mechanical basis, de-risking from a cost basis. We can have these systems factory built, factory acceptance tested, which means when you bring it to the site, all you're doing is assembling. And there's a lot that goes into assembling. I don't want to sort of say, yeah, all you do is just put it together. But the plant's been built, it's been tested, and it's assembling. We're not building something brand new on a site that is potentially remote, where we have to bring in materials and expertise and people. We're again minimizing that on-site building and on-site commissioning risk as much as we can.
You basically drop it in and then get plumbers and electricians to connect the wires and pipes and hoses and things like that.
Exactly, but you're not building the equipment. You're not, kind of welding big pieces of metal together. You're not building giant reactors. And the other key element, of course, is when we look at all of these feedstocks, they're distributed. So, woody biomass, woody residuals, they're, spread out all over the place. And so the same with biosolids and the same with digestate. So in any kind of biomass process, you're trying to balance what's the biggest economy of scale that I can get to before I start getting these negative economies of scale, because my radius of getting material starts to grow so big that my logistics costs of feedstock and, security of feedstock even, becomes a big project risk. So having a modular plant of this size, the largest one we do, the biggest individual component of this plant is called a heat tube. It's the big tube that we heat up externally, that material goes through. The biggest plant we do, that tube can still fit in a shipping container. So it can still be, brought to site relatively easily. And then, we can take it from there.
That just brief, that little diagram you have there with the pyrolysis machine, obviously it's a little caricature of it, but let's say the big one, how many feet long is it? Like if say it fits into a container, which I think are 40 feet, like is one of your units 60 feet long or something with, or like what's the sort of order of magnitude kind of size or scale of it?
Yeah, it's not too far off. So as I said, the central piece is the heat tube. And so our largest heat tube that will fit in this container is we call it a 2100, and that's 2.1 meters, 2100 millimeters. So, off the cuff, it's a little bigger than 6 feet in diameter of the tube. And then you've got a bit of a box around it. So, in terms of size, you're kind of 10 feet wide by 40 feet long, very rough. My engineering team likes precision, so they don't like me talking like that. But for visualization purposes, we can call it, 10 by 40 for the biggest kiln. And that's, close enough for this purpose.
All right, perfect. I don't know. I think we've gone pretty deep into this. Anything we missed there, or move on?
No, I think more than I was planning on. So that's great, Martin. I appreciate the
my
questions.
fault.
So just a quick, this is a picture of a small scale kiln. So this one, as we were just talking about in terms of size, the largest is 2100. So 2100 millimeters or 2.1 meters in diameter. This one is 0.87 meters, so 870 millimeters. So you can kind of see a man door and get a visual representation of what a kiln looks like. The bigger ones look very similar, just a little bit bigger in all aspects. And we addressed, I think, most of these points already. The key, of course, being the self-sustaining. We capture and recover a small amount of the syngas produced to continue to run the thermal needs of the plant. So we're not bringing in, external fossil fuel energy to create, renewable products. So we talk about outputs. We've got the gas and we've got the carbon. So on the gas, we've got two things we can do with it. I mean, really three. We can use the syngas directly. It's got good energy value, make power, offset natural gas use. But, kind of the higher value opportunities are, one, to create renewable green hydrogen. We can do this with, generally speaking, off the shelf technologies for that final hydrogen piece, because our syngas is so clean and such high hydrogen content. We're 40-45% hydrogen in our gas as it comes out.
Sorry, Fred. Your syngas, when you get the RNG or the hydrogen, all you're doing is separating it. You're not actually processing or modifying it anymore. You're just separating the molecules or the atoms one from the other.
We do a little bit of processing. So if we really want to squeeze as much hydrogen out of this as possible, we'll do what's called a reforming stage. There's a little bit of methane and some other components in the syngas. Reforming splits that apart as well into more hydrogen, so it boosts it. And then it's a separation, exactly. So, in the hydrogen case, standard is doing pressure swing adsorption. And you can see on this graphic here, this is from Ontario's low carbon hydrogen strategy, which did mention us by name, which was fantastic to see. And you can see the two pathways they've identified as being green hydrogen. One is electrolysis, which I think most people know about, but using biomass, as we talk about through pyrolysis, is a second pathway to create that green hydrogen.
All right.
The other output is renewable natural gas. So in this case, instead of maximizing and then separating out the hydrogen, really what we're doing is taking the syngas and taking that hydrogen and putting it back together with some of the carbon in the syngas to create methane, which is CH4, which is basically what natural gas is. So anyone on the call who's sort of familiar with renewable natural gas will know anaerobic digestion biogas is the first generation technology. It's fed by organic waste. Pyrolysis is second generation, so that's really fed with fiber. So that's why, we got to keep in mind, one of our feedstocks is an output of a biogas plant. And the reason we have that as our feedstock is because that's all the fiber that the biogas plant, the bugs in the biogas plant can't process. So we're always after fiber, be it wood, be it compost, be it the like. And all of these jurisdictions, these are just some of the jurisdictions, but many jurisdictions in North America have these RNG targets. And you can see I've put it, their target amounts in million gigajoules per year. And the important sort of aspect here is that in 2020, in the United States, there's 157 biogas to RNG facilities producing 62 million gigajoules, which is fantastic. It's the equivalent of 460 million gallons of diesel, not being emitted to the atmosphere. But we look at the demand, all of the USA was producing roughly what Quebec and Oregon will need in 2030. And we're already seeing, some demands on feedstock availability for biogas. So kind of the point is there needs to be additional technologies like pyrolysis that can take other feedstocks like woody biomass and woody residuals to really help be able to come close to meeting these targets and demands by these different jurisdictions.
And on the biomass anaerobic digestion, you get to squeeze in a little more of the RNG and hydrogen out of it as you sort of do it through a second cycle.
Exactly. So Mark's favorite analogy specific to the biogas space is conceptually a biogas plant will kind of take the juice out of the orange, turn that into biogas, and we'll take the pulp, the rinds, the sort of the rest of the carbon, process it and create more gas out of that. So, we, from the producing renewable natural gas, we're not really competing with biogas for kind of two reasons. One, the market is so substantial that the utilities need all the gas they can get. And we can actually be on the back end of an anaerobic digester and help squeeze a little bit more out of those facilities.
So a little off topic here, but I've talked with several RNG companies and yourselves. RNG and what you're doing from biomass, but both on the anaerobic digestion and this, to me, that seems like the lowest hanging fruit, what government should be putting, because you're stopping methane from going into the atmosphere. It's carbon that's already been released and then put back into animals or into things. So it's not new carbon that's getting emitted. It just seems, I don't know, is that the lowest hanging fruit, like in terms of economics and sort of good green stuff to do out there? Because that's what it seems like to me.
Yeah, I mean, absolutely. And I think that's why we saw the kind of first generation technologies really be all about anaerobic digestion and what to do with it. And, when we look at how gas is priced in, say, California under the LCFS, what they look at is the carbon intensity. And as part of that, they take into account the avoided emissions. So, when you look under this specific LCFS, framework currently, dairy farm through anaerobic digestion has a huge price adder to the renewable gas. So they're very negative in carbon intensity because all that manure would otherwise have gone to a lagoon and degraded into methane and gone in the atmosphere, which, methane's 22 times worse than CO2 from a global warming potential. And so what we did is we looked at that and kind of took it the next step and said, okay, you've got an anaerobic digester, but it's producing this anaerobic digestate that will then sit in a lagoon or be field applied, and that'll degrade and create greenhouse gas emissions. So by putting the digestate, the byproduct, through high temperature pyrolysis, we can actually reduce the carbon intensity score of an AD project even more, which means they can get a higher price dollars per MMBTU of gas, because that's linked to the carbon intensity. So the lower the carbon intensity, the higher the gas price. And if we're able to bring that carbon intensity down even further by avoiding even more emissions, it's a benefit to our partner as well.
All right, thanks.
Absolutely. So that's the two outputs, and of course, the other one is the biocarbon. In the biocarbon space, as I said, it can go into biocoal. So that is really focused on reducing the GHG emissions associated with using coal. And in fact, ArcelorMittal in their environmental playbook that was released in June of 2021 or July 2021, they actually show pyrolysis as a key component of producing renewable and circular carbon to feed either a blast furnace, or for those who pay attention to the steel industry and know that the Fasco in Hamilton and Algoma up in Sault Ste. Marie are changing from blast furnaces to these newer technologies called electric arc furnaces. Those EAFs still need solid carbon as part of the chemistry of creating steel. And so
because you're trying to put carbon into the steel, so it's an additive into the iron ore.
it's actually part of the reduction process. So it helps facilitate, I mean, it goes into the steel for sure, but it helps facilitate the removal of oxygen from the iron. So you kind of melt it down, but when you mine iron, it's iron oxide, FeO, and you want to pull that oxygen off of there. And that's one of the key aspects in the process of removing oxygen is called reduction. And so often in the industry, we'll be talking about our biocarbon being a biocoal, but also being a bioreductant, because it's helping reduce the iron from iron oxide to iron. And that's why you need it. You need that carbon element in there to do that process. So even in EAF, we'll need it. And for us, it's really encouraging to see that in ArcelorMittal's climate report and climate strategy, that pyrolysis is a key element of moving that forward. The other opportunities, so we use it for biocoal, bioreductant, biocarbon, a lot of industry terms that are used for it. The other is generically called biochar. So that's a land application. It's got some attributes that kind of help hold moisture in soils and helps return nutrients to soils. But by land applying it, we can also generate carbon credits through some of these voluntary markets, because we're actually sequestering soil or sequestering carbon in the soil. And when you think about it, it's really kind of like a natural carbon capture and sequestration process, because the biomass, whether it's from an anaerobic digester, a wastewater treatment plant, or even woody residuals, that will pull CO2 from the atmosphere to grow the plants that end up going through us into the biosolids or through the anaerobic digester. We turn that into a fixed carbon, and that goes into the soil. So it's really the lowest cost carbon capture and sequestration technology out there, because we're using natural elements to pull the CO2 out of the air, and then we're fixing it. So that does give us the opportunity to derive carbon credits, which is a new and emerging space, but I think it's shaping up to be a pretty lucrative opportunity as well.
All right.
So that's the output. So when we talk about active projects, we have 4 now. These are staged as well. And certainly with current market conditions, we have the ability to kind of do it sequentially instead of all at once, even though that would be our ambition to do as many as we can at the same time. Of the 4 active projects, 3 are Char design, build, own, operate. Across the 3, we'll be making 1.25 million gigajoules of RNG. So that's enough for about 147,000 Ontario homes. We'll be producing 25,000 tons per year of biocarbon. The 3 that we're showing, Saint-Felicien, Thorold, and Kirkland Lake, we can direct that biocarbon to either the biocoal, the heavy industry, or the carbon credit opportunities, because of the quality of it, of what we're making it out of, which gives us a nice bit of flexibility. Across the 3 projects, that are still highlighted here, it represents about 44 million a year in revenue once they're commissioned and operational. And as we've already discussed, it's a modular approach. So Saint-Felicien will be 1 kiln train. Thorold and Kirkland Lake will each be 2 kiln trains, but the system is exactly the same. So we're replicating it across them. So we've got some cost advantages from the engineering design perspective, that it's the same kiln size, feedstock handling, gas processing, etc. So to get into it a little bit more detail, so St. Louis Obispo, this is under development with Hitachi's Ozan and Nova H that has been. So this is a picture of their anaerobic digestion facility, and our plant will be on the back end of that, processing the anaerobic digestate. This is under development as a build, own, operate, transfer. So it's kind of a hybrid where Hitachi is a customer, but we're also able to share initially in the revenues from the project until they trigger the transfer, at which point they buy the project out from us. And from a sales pipeline opportunity, HZI has announced that they have built their 100th facility and they're building more. So this is, a great opportunity to really get into a great sales channel for getting equipment out there. This one is producing biochar, where we'll be able to get revenue from selling it as a soil product, but also from those carbon credits, as well as producing green hydrogen.
So, sorry, just going back to St. Louis. So Hitachi has 100 anaerobic digestion facilities around the world and producing RNG, and you're attaching to one of their latest ones, the pyrolysis system to extract some more green out of the rinds, so to speak.
Exactly, and this facility is Hitachi's, kind of showcase plant in North America. And so this is the one that they bring prospective clients to. They bring, Hitachi also, like us, in some instances sells plants, and in some instances does design, build, own, operate. And so whether it's a client or whether it's a municipality that they want to build the plant and own it themselves, this is the site that they tour and look at and kind of showcase the technology. So it's absolutely the one that we want to be linked into as well.
So presumably, like the Optimus hat on, is that if it goes well here, with new projects, you could be considered a valuable partner, bring in. Has there been any discussion, or you think there's any possibility that, like, hey, this worked well, we can kind of use you as a retrofit on some of our other 100 units that are out there?
I mean, both are absolutely opportunities. Certainly one of the benefits, I mean, we bring some cost reductions in terms of managing digestate, and we bring the benefits of producing biochar and some green hydrogen out of that residual material that they produce. So a lot of the discussion has been around new builds and being integrated into new projects, but absolutely for specific projects as well, to go back and retrofit and say, and that's really what we're doing at this plant is a retrofit of an existing facility. So it'll really demonstrate the ability to retrofit, how the economics work, what the outputs are, the operational burden reduction on kind of handling and moving around digestate will be shown here. And then we can go down exactly as you say, Martin, both those channels. New build, Hitachi, and we're integrated in, as well as existing facilities to be retrofitted in further.
And where are you? I believe you announced this about a year-ish ago. Initially, where are you on the development of it? And just broadly speaking, what's the timeline people should be expecting?
Yeah, so the initial kiln is being fabricated. We're expecting to deliver that to the site at the end of the summer. Part of the scope on kind of how Hitachi's managing their digestate and really how they're feeding our system has increased. So they're doing more of an automated process, which is generally a good sign. And it means they're putting the investment dollars in. That has meant that we have to do or reevaluate some of the permitting requirements. And in California, that's always a bit of a challenge. So equipment's going to be delivered, and right now we're looking at getting more of the permits and kind of the construction started through sort of towards the end of winter into spring at this point, just because of that re-permitting requirement. So that's the nature of project development in California. It's not a huge delay, and it's something that we're working with our partners on, making sure that we're sticking to the new timeline, and that this gets kicked off as quickly as we can based on those permit limitations.
With that time frame expectations, would that mean sort of commissioning in early 24? If you start at like that kind of rough late 23, early 24?
No, so the benefits of being, the modular system is that it can actually, with the permits, it can be built and assembled quite quickly. So we'd be looking at commissioning through late summer of 23.
Oh, okay. All right. Okay, so a little more than a year ago, a year from now, maybe.
Yeah, yeah.
All right. That's great. Thanks.
And so for Thorold, this is, we announced fairly recently the phase one of this project. So this is, in Thorold, which is just outside of St. Catharines, Ontario. Phase one is moving and upgrading our existing plant, and then phase two is expansion. For that expansion, that phase two, we've got our LOIs for feedstock supply, which is always the crucial piece of these projects. Building and site lease is all in place. And this particular project, once it's fully built out with phase two, we'll be processing 75,000 tons a year of woody residuals. That'll be producing 10,000 tons a year of biocarbon. As I say, it can go into the biocoal space, and a lot of it will, especially with the close proximity to the steelmaking sector of Hamilton. But we also have the ability to create carbon credits as well out of the project. This project will be, and 500,000 gigajoules a year of RNG. So overall, it's looking at about 17.5 million in revenue, the completion of phase two, and that would be about 30,000 tons a year of CO2 equivalent reductions per year from this individual project. So we look at, the project budget and, how we're going to move forward with it. For sure, we're meeting a lot of the decarbonization targets of the Canadian government and the provincial governments. And so we certainly, anticipate a good amount of support to get this project built because of these fairly significant CO2 reduction numbers that we're able to present. And those are all third-party validated and verified, and everyone knows that, they're real numbers because we didn't come up with them ourselves.
The 17 million a year of revenue, is that just off of phase one, or is that like after phase two?
That's once it's fully expanded. So to give you a size of the scales, phase one, our existing plant and some upgrades to it to be able to produce the RNG is that 870 millimeter diameter plant. The expansion will be two of the 2.1 meter systems. So it will expand pretty substantially the capacity of the throughput. And that's where certainly the big revenue number comes from. Gotcha.
And what is the rough capital expenditures of, like, I guess either phase one or two, or combined, just order of magnitude scale of the CapEx?
Yeah, the whole project, phase one, phase two combined, we're making that 17.5 million a year in revenue, is about 28 million.
Okay.
To get the project fully built out. Now, one of the kind of key elements about that is, of course, the modularity of both, as capital availability changes over the next little while. We have the ability to phase it, kind of sub-phase it. So instead of building 2 kiln trains, we can build 1 kiln train. So that reduces the production amounts to half, but it also brings a lot of the equipment-based CapEx down. Similarly, we can do the kilns and start generating biocoal for the industry and biochar with the carbon credits, and start generating revenue from that phase while we build out the RNG piece. So there's a couple of ways we can phase it further if we do start to see capital constraints around how are we going to make sure we build this project, get it to revenue as quickly as we can. We've got a couple levers to pull.
Off the 17.5 million of revenue, what would be the cash flow it would generate, or EBITDA margin, or some kind of profitability metric on the project level?
Yeah, when we kind of look, down to the cash flow from these projects, Mark can correct me if I'm wrong, but it'll be high single digits, low double digits. So the margin is pretty attractive on that revenue number.
Sorry, and as a percentage point, or as like just
I guess like dollars. So, you know,
$10-ish million of cash flow?
Yeah.
Oh, okay. Oh, wow. That is pretty.
60-70%. That's really our comfortable range.
Of margin off of the project.
Correct.
Okay.
Yeah.
All right.
So that's Thorold. That's the first one up. That's, you know, the one they were starting phase one, which is, you know, a crucial development piece for us, and looking to have all the rest of the pieces together to get phase two kicked off before the end of the calendar year.
Okay.
Saint-Felicien, we also made an announcement. Now this one is also really interesting. What we're showing a picture of here is the biomass fired power plant that we will be co-located with. And what that allows us to do is kind of build, if you will, half a plant as phase one. So build the kiln. We're not necessarily making RNG right away. The biomass plant will buy our syngas, and we'll still be making the biocarbon for heavy industry and for carbon credit generation. So again, we can get it to revenue quickly and then build on the additional RNG component as a second phase.
But they're gonna buy the syngas, which is the mixture of the hydrogen and the methane, and they'll do whatever they do with it. But there's economic value for you out of that. And then maybe in the future, you can process it and separate it, and then presumably add some additional margin to it.
Exactly, and that is the plan. It's not kind of a maybe, it's we will.
Okay.
But this allows us, you know, with kind of half the capex to get the plant started and cash flowing, which is you know, a crucial element.
Yeah.
Now we recently made an announcement about this project as well, and so for those who read it, kind of just to explain it briefly, there's the town of Saint-Felicien, there's the regional municipality, what they call the MRC in Quebec. And so there's kind of three components of the project. The one that was announced was Saint-Felicien getting funding to build a waste heat recovery system. So they'll kind of collect hot water off of the power plant. They'll create this waste heat recovery network to support both, you know, greenhouse opportunities, but also to feed phase two, which is a biomass processing facility that will be owned by the MRC. And that will dry the biomass using the waste heat that's being supplied by the power plant. And then that system, this Center for Valorization of Biomass, will be the supplier for the Char project. And so, you know, all of those elements were presented as this is how this project overall works. And so we take it as a very good sign that, you know, the first part of the three pieces is being funded. Because we're, you know, ultimately they need to have the end user to generate the revenue for, you know, the city and the region in terms of job creation and tax base and all that good stuff.
Yeah. All right.
And then the final project, Kirkland Lake, this is essentially a twin of the Thorold project. So this is phased kind of after the completion of Thorold at this point. But we do have, you know, the sawmill operator, the adjacent to the site, having an LOI in place. We have a purchase agreement, an option agreement, sorry, on the land where we would site it, and you know, we're going through kind of some of that initial permitting and you know, funding support processes to get this project moving as well.
All right.
And that's the story in kind of, I guess, 50 minutes, but it was a good guide for discussion.
Yeah, so it's my fault. I threw out all the tangents and so forth. Is there anyone else like a major vendor of pyrolysis solutions? Like there's obviously the kiln guy, but like, are you bumping up against other people? Like, what is the competitive landscape on this sales pipeline? How many guys are making proposals when you are?
Yeah, and it depends a little bit on each of the three market verticals. So in terms of these build, own, operate, making renewable natural gas and biocarbons, there's one other facility that we're aware of in British Columbia that's attempting to be built. I don't know, we haven't seen any updates in quite a while on on their progress. It's certainly a different approach. They're doing the kind of $250 million mega project. We're doing the, $15 to $30 million modular project, which I think, I think we're going to win that race and get the plants built. When we look at the biosolids processing, there's a couple of competitors out there in that specific vertical. The big difference is our kind of main competitor in that space, their largest plant is equal to our smallest plant. So we do have kind of slightly different scales of what we're approaching. And as I was mentioning earlier, they're using a pyrolysis technology where they cannot create both biochar and syngas. They can only create biochar. So the economics around it are obviously a little bit different. And then in the digestate space, there's really not any other commercially developed technology providers in that space. So, I never want to say there's no competition, because to me that just means you didn't look hard enough, because there's always someone trying to come after you. But there's not a lot of competition right now. We have a very strong, I think, market position and opportunity, provided we really take advantage of it and can move quickly on a lot of these opportunities.
I'm thinking your biggest, like with 100 million sales pipeline for projects on the go, is your biggest challenge right now just sort of getting the capital to fund all these projects and get them going? Is that your sort of the rate limiting factor here?
Yeah. I mean, absolutely, it is, and certainly with kind of prevailing market conditions, we're cognizant of what some of our alternative funding mechanisms are. Certainly, as I said, because of the ability to meet a lot of the GHG reduction targets, the ability to use some of this waste residual material, create biocarbons and biocoals, help meet the need of the RNG targets in Canadian provinces. There is some substantial government, both federally and provincially in Ontario and Quebec and in other jurisdictions, that can help support the capex of these projects. When we look at the carbon side, we're exploring opportunities to pre-sell bio coal, to pre-sell carbon credits, to bring in some upfront revenue, or upfront cash, I should say, to help build the plant. There's specific equipment finance opportunities as well to try and help balance out some of the demands. And of course, there's the traditional project finance, which could either be project debt or project equity at the project level. So, there are still some good opportunities and capital out there to help make sure these projects carry forward and are able to be built.
And I'm thinking as well, once you sort of get a little bit further down the line, once you've got one of your projects developed, like you build, own, operate, but at the same time, if you're operating it, you could still sell it off or sell off a portion, take that capital then to fund new projects and to sort of use that to get the flywheel going. And like these are kind of your hardest steps at this point. And is there still some perceived, let's say, project risk on it, where maybe it's a little harder to get project financing in that, since they're not hundreds or thousands of these pyrolysis projects out there?
Yeah, I mean, certainly, if we look at doing everything in a linear approach, Thorold is slightly more expensive capital, and because there's a little bit less of it out there. Saint-Felicien and Kirkland Lake will be a lot less expensive, because now there's that developed piece. But to your point earlier, certainly, bringing in project equity after the project's completed, generally that type of equity still has a type of a revenue share for the developer. And generally speaking, the developer still maintains the operating contract for the facility. So to kind of recycle, get the flywheel going, that's absolutely something that we're evaluating. But absolutely, once the road's built, and that's why we're really pushing aggressively on getting that built as quickly as we can. That will make the project finance opportunities, and in whichever of the different levers we choose to pull, less expensive and more readily available. Absolutely.
All right, thanks, Andrew. I think you did a great overview here, and we're patient with my questions, which I appreciate. We got questions in the audience here, so I'll start lobbing some of those off at you right here. I'm just reading them live, so hopefully it all makes sense here. What happens to pyroil? And I guess that's oil, bio oil derived from the pyrolysis system. Any pyrolysis produce syngas, biochar, or pyre oil. I understand is high temperature, but syngas can change some of the polyaromatic materials. Does it end up in wastewater? Obviously, someone who knows more about this than I do.
Yeah. No, that's fair. And, I love a good technical question. So, absolutely, to the point, it's high temperature, slow pyrolysis. So we really, really minimize the amount of bio oil or pyrolysis oil being generated, because at those high temperatures, what's happening is all of the volatile material is being volatilized. So it's turning into gas. And as a gas, it's cracking apart into kind of its constituent pieces. It's hydrogen, it's methane, it's smaller chain hydrocarbons. So we have on a yield basis, somewhere on the order of 5% of the output is in the form of an oil in our scrubbing system, our syngas cleaning system. So our syngas cleaning system, we're really looking at any oil that may condense out as we cool the gas and heavier things start to condense, as well as any carbon dust that happens to be carried through. So both of those are scrubbed out in a fairly basic, and basic in this case is good, basic wet scrubbing package. That scrubbing fluid, which is water, we do a little bit of pH control, goes through a filter, and the carbon dust and any of that oil that is residual can be separated and can be reintroduced in the kiln. That oil will then volatilize again, turn into gas again, and have another opportunity to further crack and break down into those permanent gases.
You, like from anaerobic digestion, you're left with, I forget what it's called, the sludge or that which then you process. Are there any byproducts left when you do your system, or is it basically everything gets turned into biochar or syngas and nothing's left? It's just all used.
Exactly. And so some of the things that'll change site by site is kind of what else is in the biochar. And so when I mention ash, which is not good for, say, steel making, but is great for land application, that's where we carry through potassium and phosphorus and calcium and those other elements that were in that digestate. So it kind of continues through, stays with the carbon, and has plant availability benefits. So it's a good thing.
All right. I have a feeling these are from they're anonymous questions, and they seem to have the same tone of someone who knows maybe a potential client or so. What is the maximum capacity of your modular units on a wet basis?
Yeah, and it's a good question. When we look at it, we're really looking to come into the kiln around 30% moisture. We can come into the kiln as high as 60% moisture, but that is not as energy efficient as doing some pre-drying. So, we're operating the kiln at 850 degrees Celsius, so we can use some of the exhaust heat to pre-dry material going in. So if we look at it just from the kiln boundary, we can be about 5-ish tons an hour on a wet basis at the level that we would accept it. On a dry basis, like 15% moisture, 20% moisture, will be more like 3.5 tons, 3,500 kilograms an hour, in that range.
All right. So, okay. All right. So you do some pre-drying beforehand, and then you just look at the relative cost of it'll cost so much to do some extra drying versus the extra cost of running it a little longer or hotter or whatever in the pyrolysis machine, and you optimize that.
Basically, yes. Yeah.
All right. I think we've addressed this, but these are good points to discuss. What do you expect the overall project level EBITDA margin for the 44 million of revenue generated from 3 build, own, operate projects? Will each of these projects be generating revenue?
They will be generating revenue. Maybe I'll give a Mark, since we stayed on the presentation, you didn't get much chance to speak, so I'll let Mark have a say here.
Yeah, they'll all be generating revenue, and I guess that range of 60 to 70% gross margin would apply across the board, somewhere in between. I'm most comfortable closer to the 60% level to be a little bit conservative.
And with your offtake, do you have actual offtake agreements or do you like sell your RNG at whatever kind of market price, or like how confident, like do you lock in your input and your input costs and your output revenues?
For these initial projects, we will be locking things in for longer term for that stability. I mean, you can, once gas is in the grid, you can kind of sell it anywhere. But you know, for kind of the name of the game of risk reduction, you know, having that 15-year offtake with one of the Canadian gas utilities, you know, looks a little better than, you know, we'll kind of wheel it to California and play the spot price. Although being linked to the price of natural gas in the California market, it is, you know, a attractive pricing, but from a risk reduction and therefore the ability to attract capital to build the plant, having those offtake agreements with the gas utilities is an important part, and we're substantially far along the road of having that gas offtake in place, and for the carbon as well.
How much of the economics is dependent upon, let's say, carbon credits or just higher prices being paid for RNG because they're trying to incentivize to get to their 15, 20, 30% RNG levels in that? How much is in the sort of marketplace versus sort of mandated or government regulated incentives?
Yeah, I would say once the project is operational, on the order of 65% of the revenue will be, you know, fixed based on these longer term offtake agreements, and the balance will be market driven, be that the carbon credits or the bio coal into the steelmaking world.
All right. We have another question here on like project finance and so forth. We touched on this beforehand, debt versus equity. Early stages, it's going to be different. You're finding where things go, but once you get to sort of the flywheel is going, it'll be a more, will it be like a 60, like do you imagine a 60-40 sort of debt equity kind of ratio, or is there any kind of broad rules of thumb you think how funding of these projects would work?
Yeah, let's say, you know, project 2+, you know, with the long-term offtakes and that kind of, you know, stability and kind of client that's signed up, I think, you know, 60% debt is certainly achievable. I think we could probably lever it up a little higher, but, you know, we'd evaluate that obviously on you know, what's best for the project, but 60% would be achievable. Certainly for the first one, that is going to be a mixture of different programs and products, and you know, there's a few that are kind of right at the edge of being finalized, but you know, be it, you know, government debt or government grants or private debt or private equity, as I said, equipment finance, they're kind of all in the mix for the first project. So it's a hodgepodge, but I think we're pretty much close to having it all aligned.
All right. And the question is, what price are you taking for your RNG per MMBTU in your revenue calculation? I'm guessing it really depends on your site location and some of the site or region specific areas, but please answer that.
Yeah, I mean, it does. You know, certainly what we can say at this point, because we're finalizing those negotiations, and I don't want to, you know, annoy our offtake partners if they happen to watch. But what we can point to is, you know, look, British Columbia has a cap of $30 a gigajoule. You know, in our pro formas, we would never use the cap for modeling purposes. We know that Quebec has gone forward and has asked the regulator to go as high as low $40 per GJ. And again, we wouldn't use those cap numbers, but it's sort of illustrative of what the top end is. And for our purposes, we look at what's a reasonable rate of return, because that's how the gas utilities actually negotiate what your pricing is going to be, is what's a reasonable IRR for all parties at the table to fix that price. And they've got requirements on how high they can go, what their sort of averaged RNG cost across all producers can be. And landfill is the lowest price, and anaerobic digestion is here, and will be kind of here. And then smaller projects may even be higher, but yeah, it's an interesting place, but it's generally based on the IRR projections and negotiated on a per project basis.
All right. We've gone over this a little bit, and we are running a little short on time here. Asking the timelines for each project, including milestones, permitting, equipment procurement, construction, and start of operation. That's a lot to go through, but maybe just very high level of maybe just key points on each of the project.
For sure. So Thorold, we're targeting phase 2 carbon production before the end of calendar 23, and then gas production into sort of mid 24. Again, that's, as I've been talking about, we're looking to get as much of the plant built and operational and cash flowing, before we, as part of the process of building it, so that we can get revenue quickly. So kind of late 23 on the carbon, mid 24 on the gas for Thorold. Saint-Felicien will be, I would say, mid 24 as well, because that's going to be staged a little bit. And then Kirkland Lake will be based on a little bit on how Thorold goes. So that's a little bit looser, but we would probably say into the 2025 range for Kirkland Lake, to make sure we're, using capital appropriately and not getting too resource constrained and having too many projects kind of half built along the way. The important question on permitting is we expect our permits to be all tied up or finalized, I should say, for Thorold in the next couple of months. So that in the Thorold project will not be our kind of long lead item, as it often is. We're well ahead on permitting, which is certainly an important aspect of project development of this type.
All right. What is the Char Tech's preferred length of contract term for a build, own, operate? You own them, so, but I guess the contracts would be more in the offtake and on the sort of the input contracts.
Yeah. And so on the output, on the gas side, just looking at other RNG projects, the kind of typical is 10, 15 year offtake agreements for the gas. The carbon will be shorter time frame, and as the feedstock will as well. And on those, we would certainly push for kind of in that 5-year range. And what we do for both the carbon and the feedstock is, lock in a base amount of both offtake and input material, and then have the ability to find the lowest price feedstock and the highest value opportunity for the remainder of the requirements. Now that's sort of the philosophy, certainly for the Thorold project. Again, on the de-risking side, our project partner on it is, Ontario, if not one of Canada's largest movers of biomass from Northern Ontario to Southern Ontario. And so working collaboratively with them, they're our feedstock supplier for this project for the full amount for kind of the life of it.
All right. And just because you've got 5 and 10 year contracts, the facility can run a lot longer than that. What they have, like 20, 30 year lifespan to them maybe, or? Yeah,
exactly. And so, the gas utilities, I think, would be happy with a 20-year offtake. And sort of the question is, what length of offtake do we want, so that we've locked in a really good return and revenue and margin cash flow from the project, but that, as markets change and as the price for gas is maybe substantially higher in 15 years, we can have the opportunity to then participate in that market opportunity. It is really an important aspect of it as well. And when we look at the plant itself, 20, 30-year life is pretty reasonable because there's not a lot of super complex aspects. So major parts like the heat tube, for example, in the kiln is one of the major parts, and that can be replaced, and the replacement cost is on the order of $300,000. So on a preventative maintenance replacement cycle, we can kind of have the whole plant, components of it rebuilt, refurbished as we go along. So it's not like some of the other types of plants where, like a biomass fired power plant, for example, you got this big fluid bed boiler that, you can't realistically, you can keep repairing it, but you can't realistically refurbish the whole thing through the life of it. It does have a life. The modularity of the system, I think, lends itself to the ability to continue to follow a preventative maintenance schedule and kind of have that really long project life, should you choose to kind of keep it going 30 plus years.
All right. How long does it take to build a kiln? And like someone's asking, I guess, where are they manufactured, and coming up to, like, if Hitachi wanted 50 units, like, would your supplier be able to supply that, or is that a limiting, or is that a risk factor for you that your vendor couldn't maybe supply the demand you need?
I think the demand we have, the projects we have in our pipeline, we can have it supplied from the vendor. I mean, the plant, a kiln is about 40 weeks to build and be ready, factory acceptance test ready to build, or ready to ship, sorry. But, multiple can be built at once. So it's not one kiln every 40 weeks. It's, multiples in the shop. But certainly as part of our agreements and review is, as we start to butt up against fabrication capacity, is the right and the ability to find local manufacturing to build major aspects of these kilns as well, to ensure that we do reduce that risk factor as much as possible.
All right, and one final question here. What about hydrothermal liquefaction of sludge compared to your technology?
No, it's a great question, and I've been following the research. Conceptually, it's really cool. For those who don't know, it's, instead of sort of a dry process like we do, you do it wet. So you mix it with more water, you heat it up under a lot of pressure, and that's the limiting factor. Is as you scale up something that needs to be under a lot of pressure, the wall thickness of your vessel starts to really increase, and so there are some, I think, potential scalability issues here. I think it's a cool technology. It's one that certainly we watch. But when we look at, we want to make 10,000, 20,000 tons a year of biocarbon, we want to make 500,000 gigajoules of RNG, we want to process 75,000 tons a year of feedstock to make those outputs. That's a really big, thick vessel to get the pressures that you need to get into those systems. So just like anything, that it has the right applications, but there's probably limited spaces where we're kind of crossing paths with a liquefaction type technology.
And this is still kind of in the R&D stage. Are there like commercial systems running at this point, or is it more laboratory or bench scale kind of stuff?
I haven't seen any commercial, and I should clarify, because I may have misinterpreted. I'm talking mainly about hydrothermal liquefaction from a carbonization perspective, because that's our world. In that case, we've seen some sort of pilot projects. I don't know of any commercial hydrothermal to carbonization processes. If this was more a question about, say, the Listech process, I would say it's hard to compare if it's on that kind of a process, only because the outputs are so different. We're making a carbon and a gas, and in that case, they're making a liquid fertilizer. So it's a little harder to compare. So hopefully it was either hydrothermal carbonization, which is high pressure and kind of being piloted, or a different process like Listex, which again, we're kind of optimizing for very, very different outputs. So it's much more difficult to kind of compare the two.
All right, Mark and Andrew, thank you for your patience. Thanks for all the questions and so forth. I think this went a little bit longer than all of us thought it would, so I appreciate it. Just as we wrap it up here, any final thoughts or comments?
Mark, I'll leave that with you. I think we covered almost everything, and my voice is getting close. About an hour as long as I could talk.
We covered quite a bit of ground here.
All right. Well, with that, thanks a lot,
Martin.
guys. Really appreciate it. Thanks for the update, and we'll be watching and seeing your little duck legs swimming fast under the water, and looking forward to seeing the news flow come out. Cheers.
Awesome. Thanks, Martin. Appreciate it.
Thanks.